Okay, today we're going to talk about similarity and volume. Now, when we talked about similarity and area, we talked about how things, when you have area, it gets bigger faster by square units. Well, in volume, we have pretty close to the same thing, except there's a little bit of a change. Now, here you see a picture of statues of the Oscars, which just actually happened. Now, every year they give out Oscars to people. Each Oscar that they give out weighs about 8.5 pounds. Now, those Oscars you see in this picture are obviously much bigger. If it was the same type of weight that they have from the original Oscar to that one, each one of those would be almost 2,000 pounds. Now, I know it's bigger, but how does it get to be that much more volume? And that's what we're going to talk about today. Now, when we're talking about volume, we also have to talk about similarity ratios. So we have to kind of go backwards and say, hey, what's the side ratio of things? So that's what we're going to do right here. We're going to use the side ratio and the volume ratios to kind of help us figure out if there's a pattern. So the first thing I want you to do, hopefully on your page, is to draw a cube with a length of 1, width of 1, and a height of 1. Start with cubes because that's easier. We want to calculate the volume. Since it's a cube, it's the same thing as a prism. A prism is base area times height. So if you had a cube that looked like this, you should have a volume of 1. Now, if I were to take that same cube and I multiplied each of those lengths by 2, and we drew it, we should get a figure that looks like this. What would be the volume of that cube? Well, base area times height. Base area is 4. Height is 2. 4 times 2 is 8. So now let's look at, we have a volume of 1. We have a volume of 8. We have to look at our side ratios and how they play an impact. So let's look at what's the ratio of the lengths of the sides from the larger cube to the smaller cube. And let's look at the ratio of their volumes. Well, the side ratio, we would say, is 2 to 1. Each side is twice as big as the volume now, however. Volume is 8 to 1. Because the volume of the big one is 8, volume of the small one is 1. How do we go from 2 to 8? That's something we're going to have to look at. Let's try it one more time. Let's take that original cube, let's multiply it by 3 and draw the new one. So you should have this cube. So a 3 by 3 by 3. Now we got to find the volume. So base area is 9, height is 3, 9 times 3 is 27. If we did the same thing, where we wrote the ratios of the lengths, and we wrote the ratios of the volumes, what would we see? Well, the side ratio should be 3 to 1. The volume ratio should be 27 to 1, because the big one is 27, the small one is 1. So let's look at this. How do I go from 3 to 27? How do I go 2 to 8? Well, that leads us to what our volume ratios are. Volume ratios are cubed. So we take the side ratio, whatever it may be. It could be a radii, it could be an edge length, it could be anything. Once you write down the ratio, you cube it, that gives you the volume ratio. When we did surface area or area of figures, that ratio was squared. Volume is cubed, just like the units. So let's look at our first example here. Say I told you the side ratio was 4 to 3. My first question here is, what is the ratio of the areas of the bases? Let's see, it says area. Area means squared. So what I have to do is square the ratio, 4 over 3 squared. That gives me 16 over 9. So remember, anytime you see the word area, that means to square it. Now let's look at the volume. As you see above, the volume ratio is cubed. So I'm going to take that same ratio and I'm going to cube it. That means 4 times 4 times 4, 3 times 3 times 3, What do we have? 64 over 27. So anytime you have the side ratio, if you want to find the volume ratio, you have to cube it. Now this is going to be helpful in finding missing volumes, as we're going to look in our next. Now suppose I give you the similarity ratio, and I give you a volume of the smaller figure. We want to find the volume of the larger figure. So let's look at our first example here. I've got a similarity ratio of 1 to 3. The volume of the smaller one is 10 meters cubed. So the first thing I got to know is, what's the side ratio? The side ratio is 1 over 3, same as the colon. Same works as a fraction. Now we need the volume ratio. Volume ratio is cubed, so I get 1 over 27. I need that fraction to find the missing volume. Now since the volume I have, the 10 meters cubed, is the smaller figure, that means when I set up the fraction, the 10 is on top, x is on bottom. So 1 over 27, 10 over x, you have to cross multiply and divide. You would get x equals 270. That means the volume of the bigger figure, whatever it may be, it could be a prism, it could be a cone, it could be a cylinder. All I know is that it's just 270 cubic meters. Let's try one more. Here we have a similarity ratio 3 to 10. The volume of the smaller figure is 540 cubic feet. We want to find out what's the volume of the larger one. Well, let's look. The similarity ratio of 3 to 10 means that's the side ratio. I need the volume ratio in order to finish the problem. So that means I have to cube it. So 3 to the third power is 27. 10 to the third power is the same thing as 10 times 10 times 10, which is 1,000. You can see these numbers get really large really fast when we cube it. Now since the 540 is a smaller figure, it'll be 27 over 1,000, 540 over x, cross multiply and divide. 27x equals 540,000, and your volume, after you divide by 27, is 20,000 cubic feet. So when we're talking about similar figures, when we're talking about volume, especially three-dimensional figures, it gets larger really, really fast. Make sure that you follow these examples to help you with any of the problems today. Keep in mind, make sure you pay attention to what the assignment is, finish that assignment, and hopefully you'll be able to get it done in class.